First of all, let me thank the organizers for inviting me to present my research. So as the title of the talk says, I will mainly present the results of this paper that we published with the Madrid group. So Margarita, Tony, Pietro, who was a PhD student, and our collaborators in Hiroshima University. If I have time, I will also flash the main results of this recent paper, which will appear soon in JHEP. And I will talk about, of course, the determination of the gluino condensate in SUSY Yang-Mills from the lattice at large N. Okay, so I will start with like the status before we started our research. So, okay, so we know that in SUSY Yang-Mills, so SUSY Yang-Gauge theory coupled to one massless adjoint Majorana fermion, which is the gluino. There's this pattern of breaking of the U1 axial chiral symmetry. So there's the anomaly, which leaves Z2n subgroup unbroken, which is however spontaneously broken down to Z2, and there is a non-vanishing gluino condensate which is associated to this spontaneous breaking. And this gluino condensate was computed using Nielsen calculus techniques in the 80s by Novikov, Schiffman, Weinstein, and Zakharov in two different regimes, so the strong coupling and the weak coupling regimes. And these two calculations gave different results for the gluino condensate, trace of lambda square, which is normalized in this way. I will explain it better. So by dimensional analysis, of course, this is proportional to lambda cube, where lambda is the dynamical scale of the theory, but the prefactor is different and also has a different n scaling, as you can see, when we normalize it like this. And more recently, there has been a calculation from Amber and Popitz using fractional isomptom instead, and this gave yet a third result, which yet had a different n scaling, because they performed SU2 calculation founding 2 lambda cube, and they argued that the 2 becomes n for SU Yang-Gauge group. And after our paper, they updated their calculation, where I will discuss about it later. So there's let's say, a controversy which is not fully clarified yet about the value and n scaling on the gluino condensate, and so we believe that this deserves a first principle lattice analysis in the large Yang-Gauge theory. So despite a huge progress in lattice simulation of super symmetric gauge theories in the last 10 and plus years, the lattice determination of the gluino condensate were very few and all limited to SU2. And moreover, they were all lacking a continuum limit extrapolation, which is necessary to really recover supersymmetry. And there was no matching between the analytic NSVZ calculation scheme and the lattice scheme. So we essentially bridged this gap in our paper because we provided both chiral and continuum extrapolations, and we also matched the lattice and the NSVZ scheme calculation so that numerical results and analytic calculations can be really meaningfully compared. Okay, so I want to start exactly from this latter point. So I want to really explain what are the observables that we need to compute, because this is necessary to understand how to match lattice and NSVZ calculation. So concerning the lambda parameter, the isomptom calculations are done in a scheme where the beta function is exactly known. And this is the exact expression where B0 and B1 are the first two universal coefficients in the perturbative expansion. And lambda is the tough coupling in this scheme, which I just call NSVZ, okay? Just to remember that in this scheme, we know the exact expression for the beta function. And this is, of course, the exact expression for the lambda parameter that comes out from the integration of this beta function. And this is the lambda that was appearing in this first slide, okay? So, of course, if we instead do the calculation in a generic renormalization scheme, we know that the lambda parameter changes because it's scheme dependent, and we know that this is the generic expression, which of course depends on the two universal coefficients and also from the rest of the beta function, which is non-universal. And of course, if we truncate this expression to two loops, we find a similar expression, but for different coupling, and of course, this is just a two-loop truncation, not exact. So the idea is to perform the calculation in a different scheme, which is more convenient for the lattice, and then to match this with the NSVZ scheme. And this can be done because the ratio of the lambda parameters into different schemes is always given exactly by one loop calculation. So I will show that there is a chain of ratios of lambda parameters, which will lead us from the lattice to the NSVC scheme. So concerning the gluino condensate instead, so the trace of lambda square is the so-called RGI condensate. So it's a renormalization group invariant quantity. And usually on the lattice, we are not used to deal with this kind of condensates, but rather we deal with a scheme and scale dependent condensate. So if you go to flag, for instance, you will see that the chiral condensate of the quarks is reported in MS bar scheme at a renormalization point of 2 GeV, which is a conventional choice. So what is the relation between the RGI and the scheme and scale dependent condensate? Well, in the NSVC scheme, in these papers, it was found that this is the relation. So this is the RGI condensate with this renormalization, where now we understand V0 is the first universal coefficient. This is the scheme and scale dependent condensate in the NSVC scheme, and then this factor here connected with the RGI1. So essentially this factor here cancels the scheme and scale dependence of the condensate and gives the RGI condensate. So how can we generalize this in order to compute it on the lattice and obtain an RGI result? So basically, we perform the same step that we have done for the lambda parameter. So there is also a Kalan-Semantic equation for the gluino mass, which is of course given by the anomalous dimension, which has only one universal coefficient, which is this D0. And of course, this differential equation has a RGI integration constant, which is also scheme independent in this case, which is the so-called gluino RGI mass, which is given by this very long expression, which depends on the beta function and on the tau function, and on some arbitrary constants. Now, the point is that the product between the gluino mass and the gluino condensate, the scheme and scale dependent ones, is RGI. So if these factors here cancels the scheme and scale dependence of the gluino mass, of course, its inverse will cancel the scheme and scale dependence of the gluino condensate. So this is the expression of the RGI condensate in a generic scheme. Of course, I can use the scheme that is more convenient because this in the end will be RGI. So to fix this arbitrary constant, we specialize this expression to the NSVC scheme where the tau function and the beta function are exactly known. And we recover this expression here if we choose A equals to 8 pi squared divided by 9n squared. Okay, so the goal is to just use the expression for a scheme which is convenient on the lattice, and we'll have the same RGI quantity of the analytic calculation. Okay, so now I will go to some details of the lattice calculation. So as I said, I want to do the calculation at large M. So instead of performing standard calculation on external lattices for several values of the rank of the gauge group and then extrapolating to infinity in powers of 1 over n, I will instead do the calculation directly at large M, exploiting a property of the large N lattice gauge theory, which is the large N volume independence, which was discovered for the first time in this pioneering paper by Eguchi and Kawai, where they discovered that at large N there is a dynamical equivalence between space-time and color degrees of freedom, which is essentially described in simple terms in this way. So essentially, the color dependence and the space-time dependence is codified in a single quantity, which is the effective volume, n squared times v. So if I take n to infinity, even if for a fixed finite volume, I still get the physics of the infinite volume. So the large N limit is a sort of thermodynamic limit. So if I take this idea to the extreme consequences, I can reduce the volume as much as I can, so that I can reach much larger values of n. So in particular, I can make the volume shrink up to a single space-time point. So I choose a degenerate lattice with just one space-time point. And this allows me to reach values of n which are 2 orders of magnitude larger than the typical ones which are reached in the standard approach. So there, of course, this property holds under certain assumptions, and one is center symmetry must not be broken. And of course, we know that if we reduce the size of our lattice, we go into the confined phase where center symmetry is spontaneously broken. So we have to enforce it in some way, and there are several proposals how to enforce center symmetry. And our is to impose twisted boundary conditions, so that the holonomy in the twisted directions is trivial. And this is why the proposal is known as twisted Eguchi-Kawai or TK model. So in a nutshell, this is how our reaction looks like after imposing the twisted boundary conditions, after getting rid of the space-time degrees of freedom, and after doing a change of variable. So it is very familiar because it's essentially the Wilson plaquette action, but just with a single plaquette, which is this one here. And this is the twist factor, which essentially expresses a consistency condition for the twist. And here, the gauge coupling is called B, and it is related by the typical gauge coupling using the lattice calculation beta by this relation. And of course, by asymptotic freedom, again, we take the continuum limit when we let this B go to infinity. So I want to stress two facts. So the first fact is that although this calculation is done for a lattice action, which is just 1 point, it is not true that the volume is really 1 point. It's not one lattice spacing. But the effective volume is square root of m. So this calculation is done, I mean, the results of this calculation must be interpreted as if they were done in a periodic box with size square root of m. So this is the volume where our particles propagate, okay? And the second thing is that we use the so-called symmetric twist. So we take n, which is the square root of a prime number, and of course, the square root of n is L. Sorry, the square, not the square root, sorry. And the flux here that appears in the twist, K, is also scaled with n, and this is done to minimize non-planar finite time correction. So in order to ensure that we don't never go in the center symmetry broken phase. And finally, this is the expression for the adjoint TEK Dirac operator, which is of course needed to simulate adjoint fermions like the gluino on lattice. And of course, it looks like the Wilson operator in normal extended theory, except for the missing space-time matrix here. So concerning the simulation, of course, we must include a dynamical gluino in our simulation because, of course, the gluino is an adjoint fermion, so of course its dynamic is not quenched in large n. So we need to use the well-established techniques which were developed by the Desier and Regensburg collaboration to perform simulation with the dynamical gluino. And of course we must use techniques which are akin to those used in lattice QCD with dynamical quarks. So in particular, we have a dynamical massive gluino, discretized, as I said, with Wilson fermions. We use the hybrid Monte Carlo algorithm, and we also use sign-quench simulations because in order to have a dynamical gluino, we need to include the Pfaffian instead of the determinant of the Dirac operator in our simulation. But at fine lattice spacing, this is not positively defined. So we just take the modulus in our path integral distribution and just reweight to keep into account the sign quenching. But in practice, we saw no occurrence of negative signs for the Pfaffian, so in practice we don't do this reweighting. And finally, according to the proposal by Kaplan and Curci and Veneziano, of course, the lattice and the mass of the gluino break supersymmetry. But if we take the continuum and chiral limit, we recover supersymmetry. So the supersymmetric limit is the chiral and continuum one at the same time. Okay, so how do we take the chiral limit? So in general, for Wilson fermions, we have a free parameter, which is kappa, the Hopin parameter, which controls the gluino mass, and the vanishing gluino mass limit is obtained when kappa goes to a certain critical value, kappa critical. But in practice, kappa critical is reached by monitoring the so-called adjoint pion mass. So what does it mean? So the adjoint pion is not a physical particle of the spectrum of the supersymmetric theory, and is a particle which is only defined if we supplement SUSY with an additional valence quenched gluino. So this seems weird at first glance, but actually this concept can be put on very solid theoretical grounds in the framework of partially quenched chiral perturbation theory, and it was done by Munzer and collaborators in this paper. And in particular, they write down what is the effective chiral Lagrangian for this supersymmetric theory with the additional quenched valence gluino. And they can find an expression at next leading order which relates this adjoint pion mass to the gluino mass. So this equation looks very similar, at least a leading order, to essentially the Gell-Mann-Oxener relation. And there's a different next leading order because, as you can see, there is no chiral log due to the adjoint nature of the gluino. And concerning instead the continuum limit, we perform the very typical scale setting that people do on the lattice. So we fix the scale from the gradient flow of the action density. So in particular, we fix the value of the flow energy density at a certain time. So the typical choice T0 is obtained when we cut this energy density at a time of 0.1. But instead we chose a different time, 0.05, because it suffers for less finite volume effects. But we could determine the ratio of the scale T1 and the typical scale T0. So in the end, this is not a problem. And moreover, this is also irrelevant for the final results because, of course, this scale will be used to determine sigma and lambda in physical units. But in the end, we will just calculate the ratio between sigma and lambda cube. So in the end, this scale will just drop out. And this is just a depiction of the calculation of this scale and X extrapolation to the chiral limit, so to the supersymmetric limit. Okay, so now let me discuss how we computed the gluino condensate. We followed two methods. So one is essentially based on partially quenched chiral perturbation theory because, as I said, if we consider this adjoint pion particle, we have a sort of Gell-Mann-Oxener-like relation, so we can read the gluino condensate from the slope of the pion mass as a function of the gluino mass. And then we also consider this spectral method, which is set based on Minkowski relation, which essentially allows you to obtain a condensate from the low-lying behavior of the Dirac spectral density of the adjoint operator. And there's an extra factor of 2 here because of the Majorana nature of the gluino. So this is method 1, so the one based on Minkowski relation, which is practically implemented using the Jussy-Luscher method. So essentially, we solved numerically the eigen problem for the Dirac operator for the first few modes. We used 100 modes in this case. And then we count modes below a varying threshold, capital M, to obtain the mode number. So this is essentially the mean number of eigenmodes that we find below a scale, capital M. And then we use this relation to relate the slope of the mode number as a function of M to the chiral condensate. This essentially stems from the fact that the mode number is essentially the integral of the spectral density, and so the derivative of the integral is just the spectral density itself. So this is equivalent essentially to the Minkowski relation, but written in a way that is convenient to calculate on the lattice. So this is how we extracted the slope by performing a fit near to a value of capital M, which is of the order of the gluino mass. And this allows to obtain a bare condensate, which according to the renormalization property of this threshold capital M is sigma r divided by Zp, where P is the pseudoscalar renormalization constant. But we were also able to determine a non-perturbative result for this ratio, where Zs is the scalar renormalization constant. So in the end, we can convert this to sigma r divided by Zs. And the reason why I do this is that also from the Gell-Mann-Oxener relation, we obtain a determination of the bare condensate in terms of Zs, so of the scalar normalization constant. In this case, as I said, we read the gluino condensate from this slope. So in this figure, we are fitting the pion mass square dependence on the bare gluino mass. Of course, we also need f pi, but we were also able to compute it in standard way from the same correlation function that were used to obtain the pion mass. Okay, so now we have two determinations of the chiral condensate, which need to be renormalized. And then we also need the lambda parameter, because, as I said, we want to compute the ratio between the condensate and lambda cube. So this is done essentially by using asymptotic scaling, so essentially by using this equation, which follows from the two-loop truncation of the general expression that I showed in the beginning. So, this one here, essentially. So what is typically done is to move from the lattice scheme to a so-called improved scheme, so improved lattice scheme. So we define our Baire coupling, our improved Baire couplings from the Baire couplings B that appears in the action, but also from the average value of the plaquette P. So essentially from the average, from the energy density, from the action density. This is because all these definitions, if are expanded perturbatively, will give, of course, the same answer at leading order, so just the Baire coupling. But of course, we are also inserting some non-perturbative information in our definition of the improved couplings. We have tried 3 different definitions of the improved couplings, and they all gave very similar results, which are then extrapolated towards the continuum limit, and they converge to the same result. So we just impose that they have a common continuum limit, and this is our final result. So of course, if we use improved couplings, this lambda parameter would be in a lattice improved scheme, but thanks to known results in the literature, we could obtain the ratio of the improved lattice coupling to the standard lattice coupling, which is then matched to MS-bar scheme from an old paper by Peter Beige. And then the MS-bar scheme is then matched to the NSVC scheme thanks to the results of this paper, which which calculates the one-loop ratio between these 2 couplings. So in the end, by this chain of ratios of lambda parameters, we arrived at the expressing the lambda parameter in the NSVC scheme, which is given, as I said, in terms of this gradient flow scale, which in the end will drop out. And just for comparison, I also give the MS-bar scheme, which is the one that people typically use in lattice QCD calculation. Okay. So now our last step, we are almost done. So as I said, we have these Baire determinations. We have 2 Baire determinations of the condensate. So we normalize it using 2-loop perturbative expression for ZS in the MS-bar scheme at a renormalization scale equals to the inverse lattice spacing. So this gives us the renormalized condensate in the MS-bar scheme at a lattice scale, mu equals 1 over A. And then we use this general expression for the RGI condensate truncated at 2 loops in the MS-bar scheme in order to pass from the scheme and scale dependent condensate to the RGI one. And this is essentially what we get, This is essentially what we get at two loops in the MS-bar scheme, where the D1 coefficient, so the next to leading order coefficient of the perturbative expansion of the anomalous dimension, is known in the literature. So we perform this calculation to obtain the RGI condensate, and then we divide it by lambda cube to put it in physical units. And we repeat this calculation for several values of the lattice spacing and of the gluino mass, and for 3 values of n, which are 169, 289, and 361. This is results from the pion mass, and this is results from the spectral density of the Dirac operator as a function of the lattice spacing, B, and of the gluino mass, which is expressed in terms of the pion mass. And as you can see, all the results fall on top of each other for different values of n. So already this result tells us that our results rule out all but the weak coupling analytic calculation, because the other 2 competing results gave different leading order scaling for n. So the last step to conclude is to just extrapolate our values to the supersymmetric limit. So we take a combined chiral and continuum limit of the 2 determinations, which is expressed by these 2 extrapolations here. This is the weak coupling result for the coefficient connecting the RGI condensate and the lambda cube parameter. And as you can see, once we take the supersymmetric limit, both determinations which differ at finite lattice spacing and finite gluino mass, they both converge to the same result, which is in perfect agreement with the weak coupling result. And this is in particular our final result, where we both took into account statistical errors and systematic errors, which come from our perturbative normalization and the truncation at two loops of the RGI expression. And then, after our paper came out, Amber and Poppitz updated their computation with fractional instantons in this paper, which was recently published, and they also found a value in independence, which is in agreement with our results. So, if I have still a couple of minutes, so this concludes the part on the gluino condensate, which was the main topic. But I want also to advertise that we also have a paper which will appear soon on JHEP, where we also computed in the same simulations the mass of the gluino-gluo bound state LRGen. So this is a member of the lightest supermultiplet, which is made by the lightest glue ball and also the lightest flavor singlet meson, so the gluino-gluino bound state. So for n equals 2 and n equals 3 and color, the formation of the lightest supermultiplets was checked on the lattice. In our calculation, for the moment, we only could get the gluino-gluon mass, large n, but as you can see, our large n results, this is the extrapolation towards the supersymmetric limit. And once we take the supersymmetric limit, we find a result which perfectly fits with the n equals 2 and n equals 3 results, and is compatible with the presence of very small 1/n square correction. So if we assume supersymmetry, our result for the gluino-gluon bound state mass is a prediction for the mass gap of large n supersymmetric theory, and this is the result in terms of the NSVZ parameter. Okay, so I'm done. Thank you very much.
Thanks for that nice talk, Claudio. Questions? Igor?
Yeah, thanks. Very interesting. I have a couple of questions, comments. One is, so is this the lightest, this fermion is the lightest bound state here? Or?
Yes, this is the ground state in this channel.
And have you been able to measure the string tension?
We didn't measure it, but in principle we could measure the string tension.
But you don't yet have a result.
No, of course it's very difficult with dynamical fermions.
Oh, it's
okay. But I mean, in principle it can be done. There is no obstruction in principle. It's just easier to set the scale with different quantities like the gradient flow action density.
Yeah, I just want to mention that there is a baby version kind of this theory, which may be easy for you to study with your method. I already mentioned it during Margarita's Zoom talk, and Silvio Pufu talked about it. It's 1 + 1 dimensional SUN with an adjoint, say, massless Majorana fermion. And for small n, we were able to get some values of gluino condensate and also Georg Bergner and collaborators. But would be interesting to apply this large n method to, it's probably much easier than numerically than one.
Yeah.
But there is a conjecture even for n dependence, which thinks stacks for small n and
yeah, I think it would be very interesting.
Yeah, in that model, actually, string tension happens to vanish for
the string tension vanishes.
Yeah, the string tension vanishes, but there is mass cap and there is a gluino condensate. A very peculiar 1 + 1 dimensional model, but
okay.
Thank you.
Thank you for the comment.
So did the Amber and Poppit's revision indicate what happened in the first version?
Yeah, so basically they performed a normalization which was done for a different setup of the twisted torus. So they were missing a factor of n. in the modalized
Having
space.
to do with the size of the effective size of the.
I think it has to do
or?
with the modalized space, no? They were counting wrongly the number of degrees of freedom.
Okay.
So they were missing a factor of n, which is exactly the extra factor that they had in the first paper. No, because in our one-side approach, we cannot measure like global states mass. Well, they were done not in the reduced lattice, so they were done in standard calculation, so they could measure all the mass of all the three members of the supermultiplet, and they found that in a supersymmetric limit they have the same mass. Yeah. So here I'm just showing the comparison of the lightest gluino gluon bound-state mass, but for 2 and 3, well, if I misrepresent your results, you can make a comment, but the mass of the three members, they all agree in the supersymmetric limit. So exactly. So even if we just have one state, our result is compatible with the mass of the supermultiplet for 2 and 3. So this is why I said if you assume supersymmetry, which I think is a reasonable assumption, then we have a prediction for the mass gap at large n.
So Arkady, why didn't strong coupling work?
No, I mean, I'm probably the only representative of an SUSY here. But no, but I wonder, you know, about this large number 9, right? Which you got, because, you know, one of these ideas which we were discussing in application to QCD was that the existence of different scales, that it could be, you know, kind of, say, particular for glue balls, that this characteristic scale associated with glue ball is much larger than, say, a low meson channel. I'm not sure whether it's related, but just the amount that having this 9 here, you know, just gives me a collection of this. So I wonder, do you think that could be something here?
I never thought about that, but about this, I want to point out that we use a different normalization for the lambda parameter with respect to what you have used in your analytical calculation, because we follow the QCD convention. So we have an extra factor of B0.
Yeah.
So if we use your convention, this would amount to basically a factor of 3. So this would be more in the domain of 2.
I see. So it would be not that.
Yeah, it would be order of lambda, yes. But we use the convention of lattice QCD, which has this extra factor of B0 below. So this is why this result is inflated.
Okay, thank you. No, but the answer to the question was long before, yeah.
Okay, you already had a preference for weak coupling from a long time ago? Okay. Or
it was an issue that was very much discussed.
Yeah.
So not that I'm going to discuss it now.
Okay.
There's a question there.
You want to just go there?
Just a question about the continuum. Is there an idea why where this mismatch came about? Could it just be related to this prefactor A? So just some implicit assumption of the equilibrium.
So you mean the mismatch between strong and weak coupling?
Yes.
So, okay, so the way I understand this is that this prefactor essentially gives you a factor of 1 over n squared, which is the naive normalization that you would imagine, because this is psi psi, so you would imagine that this goes as the number of degrees of freedom of the fermions, so you imagine that this would go as n squared. So I think that a larger limit which is non-finite with this normalization, I think that would be a violation of the naive counting of large n. So I don't think that this is the origin of this discrepancy. I think there was an argument about falling apart of clustering to try to explain why the strong coupling. I'm not an expert, so.
Issue with cluster decomposition or something like that.
Yeah. Because this comes from like the calculation of trace of lambda squared n times, and then if you assume clustering, this is trace of lambda squared to the n, and then you take the nth root. So, yeah. And this gives a different n scaling.
All right, any other questions? Okay, let's thank Claudio for another great talk and the final talk of the meeting. So thanks for everyone for participating, and it's been a great conference with lots of lively discussion, and of course thank you to the KITP for hosting it, and safe travels.